Thank you for the kind invitation. I just came back from Talia Arconi's talk, and I realized I don't have enough pandas and tips how to reduce your effect sizes, and I apologize for that. So, let's... Okay. Let's talk about MR data analysis. In theory, how do you approach the problem? Well, we acquire our data, and then we diligently do quality control. Then we develop an analysis pipeline using existing tools and literature. And wait, before we go to the next step, we probably are not living under the rock, and we did see the news, and we know that the science is broken, and we have reproducibility crisis, and it also contributes both to replication and reproducibility. So let's amend this second point, and we want to develop a reproducible pipeline. So we will help people in the future to replicate our effects. And then we're going to run the pipeline, and then we're going to share the data with the whole world. Yes, everyone agrees this is how things should be done. So in reality, things might be a bit different. So quality control often is difficult. Looking at all those images is time-consuming, and I'm sure all the physicists did their job well, and it's just all great. And then the pipeline, well, maybe it's not going to be that completely reproducible, because that's also very time-consuming, and putting things into containers or whatnot, it's just hard, and papers need to come. And then we have to run the pipeline, and then we realize that actually running that fancy surface reconstruction on our laptop that is 5 years old, that might take a few weeks. So let's just do something simpler that actually our equipment can do. And finally, sharing data. I mean, like, what is it in for me? All right. So, of course, I'm exaggerating, but I hope you get the point without pandas. So the question is whether we can somehow build a tool or a platform to help with those first 3 points, and with doing that, incentivize people to do point number 4, share their data. And this is what we attempt in OpenNeuro. So in short, OpenNeuro is nothing else than a science-as-a-service platform. So it's a web service that allows you to do data analysis on it. It's somehow similar to CBrain or MRI Cloud or Mint or Flywheel. It is also an evolution of OpenFMRI. We've spent a lot of time thinking about how can we take OpenFMRI to the next level. And one of the core components of OpenNeuro is the ability to upload, manage, and share your data. And this is all based on brain imaging data structure, which is a standard that, together with the community, we've proposed last year. And the core tenet of this data management are immutable data snapshots. So you can upload your data, you can modify it, you can make additions, but each time you want to run analysis, you have to take a snapshot of it. And that snapshot cannot change, so you can always go back to it. And we've built tools into the platform that help you validate the data before you upload them, as well as deal with trivial but important things like resuming upload when your laptop dies and things like that. And then the most important and exciting aspect of the platform is running your analysis. And those are predefined packaged apps, as we call them, because we want to make all of this sound cool. And those are based on BitZap's framework, and those are containerized workflows, which I'm going to talk about a little bit later. And we try to build up a repository, a catalog of different analyses that people already do, but now you can do them online for free without having to, keep your laptop open for a week. Okay, so I do not have a live demo, but we can watch me running a cursor 2 weeks ago. So this is the steps you have to take to run a job or an analysis. There's a drop-down menu from which you can select which application you want to run. You can read about it and different modalities it supports, and each application have different parameters you can select. So for example, here, we can restrict our analysis to, for example, a subset of participants in the data set we've uploaded previously. But we can also leave it empty, and that will lead to the default behavior, which is running the analysis on all participants. We click a button, and somewhere in the cloud with angels, the job runs, and we can check its status on online. And basically, right now we see it first uploading and then running. But when it's finished, we get an email with a link that takes us directly back to the website, and we can explore the results. So I'm going to talk about different types of apps, and each of these apps have different results because dedicated to do different things. We can remind ourselves about the input parameters. We can also look at the logs, very important and handy when you have to debug something. And we can also interactively view the files created by this particular pipeline. So the one I run here was a preprocessing pipeline, also developed in a lab and presented at this meeting by Oscar Esteban. I encourage you to check it out. It's called fMRI Prep. And this app produces interactive reports that show you, for example, here, the quality of co-registration between EPI and T1. So it's not only running things that are black boxes, but also being able to validate and check whether all of these preprocessing steps were performed correctly. You can not only view the files, but you can also download them for further analysis on different platforms or your own computer. Okay, so there are many more apps, and we are growing this collection. Right now we have support for in-house build fMRI Prep for fMRI preprocessing, MRI QC for quality control, CPAC, which is built by Cameron Craddock's lab for connectome analysis in resting state fMRI, well-known and loved FreeSurfer for surface reconstruction, Nutmeg for deriving connectivity graphs from diffusion data, and SPM, which I presume I do not have to introduce to anyone. And we are also close to deploying apps, more apps such as QAP for even more quality control, OPNI, which is an implementation of NPERS framework for optimal preprocessing. There's also an aptly named package called Automatic Analysis by Tibor Auer, and Maggot Brain for doing subcortical and cortical segmentation, Tracula for diffusion analysis, Broccoli, the super optimized Anders Eklund toolbox, and a very exciting Baracus, which will allow you to estimate brain age from your MRI data. You are probably all curious because this is informatics session, so we have to nerd out a little bit how all of this works. So right now we're hosting is on Amazon Web Services, and we have an EC2-based front end with Cytron database, currently maintained by Flywheel, and a custom built React-based front end. And then the data gets pushed to S3, and it's being currently run on AWS Batch, but we are planning to extend it to CBrain, Open Science Grid, and potentially Xseed. And how all of these apps are being run? They're basically being pulled from Docker Hub, and they are maintained and provided by developers themselves. And that act is part of the framework we proposed last year. It was recently published, called BidsApps, which combines putting all of the binary dependencies of each of these complicated workflows into a container and adding a wrapper or an interpreter that allows each of these existing and well-tested pieces of software to understand the BIDS dataset as an input. Ooh, that was a spoiler. All of this is also all open source, and each of components of this platform we try to develop to be as reusable as possible. So for example, the validator that is being run on the dataset before you even start uploading it is a standalone piece of JavaScript software that could be integrated in your applications or run standalone from command line or from the browser. BitZaps as well are independent and can be run either independently or also integrated into platforms. The same goes for the front end and execution engine, and you can find all of the source on our repositories. And it's also great to see the synergy of this because not long ago, actually a couple of days ago, I saw this, which is the NIMH own deployment of OpenNeuro, which was basically possible thanks to the fact that all of this is open source and people could build on top of it. Okay, so going back to our problems and how we hope to improve them, having immutable data snapshots and software containers that are strongly versions gives us reproducibility. And this is basically done without the user having to put in any extra effort into doing data analysis. And now, incentive for sharing. The platform is completely free for anyone to use, although when you start using it, you have to agree that after a grace period of 18 months, the data you've uploaded to the platform, which is initially private, will be made publicly available under a CC0 license. And we hope that by providing the free service of data management and data analysis, we will incentivize researchers to share their data. Well, we have a few more things to do, obviously. Right now, we have a collection of apps, and we hope that this will grow and will be also allow to chain apps. So in other words, build apps that work on top of each other. And we also want to extend our computational backend capabilities to system beyond the one particular cloud provider. But most importantly, since this is the informatics crowd, if you are developing a pipeline and you would like this pipeline to be easily available and accessible to users with all credit given to you, get in touch and we will turn it into a BitZap and deploy it on the platform. And with that, I want to thank all the people involved in my lab, all of the BitZaps community, and the Squishy Media company that helped us make this platform beautiful, and Laura and John Arnold's Foundation for funding all of this effort. Thank you so much.